Nice to be here, thank you, and good to see everyone. So the presentation this afternoon, mechanisms versus covering law explanation. And Nancy and I are going to claim this is a false conflict. So this is a joint presentation between Nancy Cartwright and myself. And so we split it into two parts. And we're going to start off, I'm going to kick off the first part by setting out our thesis. And then Nancy is going to address various concerns on both our sides and the mechanist side concerning the thesis. So, right, our thesis then. So the central thesis is very straightforward. We claim that much explanation is in fact covering law explanation. Our focus is on cases where mechanisms explain regular behavior. So we have in here, the sort of cases where mechanisms give rise to regular input-output regularities. So for instance, a neuron receiving neurotransmitters particles at one end may then at a slightly later time release neurotransmitter particles from the other end, and there's a regularity between the receipt and the emission. Or, for instance, one that I'll come on to discuss is the elliptic movement of planets in orbit, so Kepler's law. So we think that these cases are everyday cases of mechanistic explanation. They include many, perhaps all of the standard cases. So a word on mechanisms before we kick off too much, just to make clear. So Nancy Cartwright in the Dappled World in 1999 set out the idea of a nomological machine, and she defines it in this way. A nomological machine is a fixed enough arrangement of components or factors with stable enough capacities that in the right sort of stable enough environment will, with repeated operation, give rise to the kind of regular behavior that we represent in scientific laws. Okay, so we are, Nancy and I are happy to call this a mechanism. Now, of course, there are a variety of notions of mechanism on the market. There is the step-by-step type mechanism, which Dan Steele favors. There's John Elster's type mechanisms in the social sciences, and then there's the invariance type of mechanism, which Woodward talks about. We think our account here is closest to that of the new mechanists, such as Carl Craver, Stuart Glennon, of course, and Bill Bechtel. And so we think that when we characterize a mechanism, giving rise to regular behavior, we can do so in this sort of way, that we can cite parts, a set P of parts in some arrangement A, which give display features a set gamma, and when the mechanism operates repeatedly without interruption, it gives rise to a regular behavior B, so that P, gamma A and B characterize the mechanism M. And hopefully that sounds pretty familiar to the new mechanist way of thinking. We think it's very much on the same page. So what is mechanistic explanation? Here too, hopefully we're all on the same page. We think a mechanistic explanation explains regular behavior by laying out the parts, their structures, their arrangements, the interactions and the activities, and so forth. But we also think that a mechanistic explanation goes further than laying them out. We think it often makes clear why that structure, operating in that way, gives rise to the regular behavior which it does. And in order to do that, we believe it often invokes laws of what the parts can be expected to do together in the salient context. And so one way of, and when the laws of behavior of the parts are identified, then the explanation is a covering law explanation. So in a sense that comes back, that is our central thesis, right? That we're going to propound. So in a sense, mechanistic explanations are a subset of covering law explanations. They are covering law information explanations in which the facts about the about the parts, their arrangement, the features, and the interactions, right? So that's the claim. So I'm sure everyone here has a pretty good idea of what we mean by covering law explanation, but just to step back again and just make sure we are all on the same page with this, let's just thought I'd set out Carl Hempel's account, which says that a behavior B is to be explained by showing B is to be expected by reason of laws and facts related to B. So here's the picture, standard, as I say, Hempel account. They have a set of particular facts, C1, C2 through to CK. You have a set of general laws, L1, L2 through to LR. And then you have a deductive argument. And the conclusion of that argument, B, is the explanandum. The particular facts and general laws are the explanans. So again, a point which I think was probably consensus is that there is the new mechanists' view is, standardly at least, that mechanistic explanation is very different from covering law explanation. And just to give a couple of examples of claims to that effect, although, as I say, I don't think this is a controversial view, but Stuart Glennon, for instance, says new mechanists are of one voice in seeing mechanistic explanation as an alternative to covering law explanation. And again, Carl Craver and James Tabery say this: according to the covering law model, explanations are arguments showing that the events to be explained was to be expected on the basis of the laws of nature and the antecedent boundary conditions. Mechanists, in contrast, insist explanation is a matter of elucidating the causal structures that produce, underlie, and maintain the phenomena of interest. So here, of course, the emphasis is on the in contrast. On the one hand, one has covering law. On the other hand, one has mechanists explanation, and the two are distinct. So we, on the other hand, don't see this distinction in the same way or so clearly. We think many mechanistic explanations are indeed covering law. But just to be clear what we're saying here, we are not saying by any means that all covering law explanations are mechanist explanations. There are indeed many we think that are not. Nor are we saying this, that everything that fits the covering law model is a good explanation. Certainly there are deductive arguments that fit the covering law which aren't satisfying explanations at all. So we say many, and indeed all the standard examples that we've seen, mechanistic explanations are covering law explanations. That's our claim. And more than that, they are explanatory because they are covering laws. So on this view, then, the covering law explanation here, B, the behavior is to be expected because of the mechanism, where the mechanism can be laid out in terms of the parts, their features, and their arrangement. So to step say that just a little bit more carefully, let lambda be then some set of principles, laws, we use the terms interchangeably here, principles which govern features gamma in arrangement A of parts, right? So lambda is here the set of laws or principles. Then lambda fills in the laws and principles in the covering law model. On that line that we had, it's the L's. The matters of particular fact are filled in by the facts about the mechanism. That's to say, the set P of parts, their arrangement A, and the types of features which the mechanism displays, so the interactions and so forth. And then once we have those principles related to the parts, and we have the facts about the arrangements and so forth, then we can deduce B. B is to be expected given the set of laws and principles in the particular facts. So the particular facts then specify the underlying causal structure that gives rise to the behavior. And where that's the case, then the explanation we believe is accords with mechanistic explanations. So again, just to step back and make clear here, we are not in this presentation discussing the nature of laws or principles. We are being completely neutral about that. We do discuss it elsewhere. Many people, of course, insist that the laws must be exact laws. Well, if there are any exact laws, we'd be perfectly happy with them. Sandra Mitchell suggests pragmatic laws, and that seems fine to us. Of course, philosophy of science now deals increasingly with causal laws. That's fine. Nancy Cartwright and other Powerists talk of tendency laws. Yep, all good. And of course, ceteris paribus laws are a huge and well-discussed topic, and we are happy with them as well. So we're not here talking about the nature of laws. So not all covering law explanations are mechanists, and perhaps the focus on mechanists on covering law explanations that are not mechanists is one of the reasons for mechanists rejecting the idea that covering laws are often mechanistic explanations. And here's an example then of a covering law explanation that is probably not mechanist. We might ask this question: why does this neuron transmit a message? And we might give this as an answer, as by way of an explanation. Ceteris paribus, all neurons transmit messages. So that may well be a covering law explanation, but it's certainly not a satisfying mechanistic explanation. And we suggest the reason not is it doesn't make transparent the role of the parts and the arrangement, etc., of the mechanism. So perhaps it's the focus on cases like this that make the mechanists uncomfortable with covering laws. And what we see here is often the facts about the mechanism are lumped under antecedent conditions or boundary conditions, so they're not apparent. So, okay, so to give then an example to help sort of show what we're talking about here, let's look at the elliptic orbits of planets, Kepler's first law. So here we might start then with Newton's law of motion, F equals ma, F equals mv dot, and we would need, in a particular case, to start with also some boundary conditions, which might include the value little of the mass and the initial value of the velocity. And then we're going to solve the differential equation to get the orbit once we have a function f. So you write down f, and you solve, and you get out the planets. And ostensibly, that really doesn't seem much like a mechanistic explanation. It does seem more like a covering law explanation. But what we want to note is that in order to do this, to fill in f, the force function, we need the functional form of the force, and that needs to have regard or to be derived from the structure of the mechanism. So in this case, here's a picture of the sort of mechanism that we might have regard to. And it's clearly a very simple mechanism. It has two parts. One is a large mass labeled capital M, and one's a small mass labeled small m, and they're a distance apart. So a very simple diagram of the mechanism. And there's some features here too. which are the magnitude of the large mass, capital M, the magnitude of the small mass, little m, the amount of distance between them, which we've written here as r. And then also we need the velocity, or the initial velocity at least, of the thing, which is here, r dot away from capital M and r theta dot orthogonally to that, okay? So now, because we have this arrangement and the parts set up in this way, we can now make use of Newton's law of gravity to write down the functional form of F. Because with this setup in mind, we know that little m has a force on it, and that force is directed towards capital M, so we know its direction, and its magnitude is gmm upon r squared, so we know its magnitude and direction. And we can now write down the differential equation of motion, which is in play, and solve that to take out, to derive Kepler's laws. So the behavior is deduced from the facts about the mechanism and the laws of motion and the laws of gravity. Now, if we start with just the differential equation, we just start with the equations and solve it without recognizing the underlying mechanism, then the explanation doesn't look like it's very much of a mechanist explanation that we suggest it is. Okay, so much then for our thesis. I'm now going to hand over to Nancy, who is going to outline a discussion of the concerns.
Can you see the screen?
Yes, we can, yes.
Sorry, okay. It was supposed to start at the, okay, thank you. Did John do that? No, I don't see how I could. I also need to get you folks out of the way, thank you. The part 2 is on our concerns and mechanistic concerns. Oh, sorry, so I've got to run through all through these. I tried to fix it so that didn't happen, but. Well, so our concerns and mechanistic concerns, and I'll start with our concerns, which are the big one, the big question, why we got interested in discussing this in the first place is to answer the question, how do mechanisms explain? So the mechanism in the sense of ontology as opposed to the model of the mechanism is supposed to explain the behavior that is in the explanandum. How does it do so? And I think it's useful to think in terms of 2 different senses of X, whatever your explanandum is, explanans is. X explains B. One is in the material mode. We explain X explains B by establishing that X is actually responsible for B in some sense in the world. And the other is the formal mode by showing that B is to be expected given X. So I want to keep these 2, we want to keep these 2 different senses of explanation both in play. When we think about the material mode, the covering law explanations, then laws are cited. The laws that are cited are responsible for B's occurrence given the facts of B's setting and B's activities and interactions, etc. In mechanistic explanation, it's the activities of the parts in the arrangement of the settings. That's in some sense, we have to think of what the right terminology is, and it's disputed, but it gives rise to, constitutes, causes B, or is responsible for B. Sorry, a dreadful cold. Now, let's think about material mode mechanical explanations that aren't covering law explanations. So consider, sorry. What would such a thing look like? Well, it would be the case for M. We have a material mode. We have an explanation, an explanans, a mechanism we cite. M material mode explains B, but it does so without the principles governing the parts as they're arranged, explaining B. So we say that M explains why the behavior B occurs, but it doesn't, but it does so even though the principles that govern the activities of the parts as they're arranged doesn't explain B. That's what material mode mechanical explanation that isn't a covering law one would look like. And we think this is perfectly possible. It's a good use for the term emergence. Emergence is again a controverted term, but this is a good use for it, where the mechanism explains the behavior, but there's nothing about the principles governing the activities of it, but the principles governing the activities of its parts as they're arranged, etc., just aren't enough to account for B. Now you can have evidence confirming this kind of fact. Let's just back up a minute. For instance, you could have you outline you find a bit of the world, you isolate a bit of the world, and you find that when triggered in a certain way, it always gives rise to regular behavior. You see this again and again. You do the kind of thing that Stuart and others have suggested, and you prod it, or you start taking, and you really look to see and study the parts, and you start rearranging them, and it doesn't give rise to B. You take pieces out, put pieces in. Anyway, you could have good, really good empirical evidence that this mechanism explains the behavior B, even though it doesn't do so under any covering law account. Now, that I think is perfectly possible. I don't actually know of examples of it. The cases I look at in physics and economics simply aren't like that. And it doesn't seem to be true of the sort of standardly cited biological examples in the philosophical literature either. But we don't want to rule out that that's possible. We do want to claim that a large number of the standardly cited ones are indeed covering law explanations. Okay. So let's think about formal mode explanation. Why expect B when M operates? We're now not looking at what the world is like, but about our reasons for expecting B when M operates, a sense of explanation of, now we see why it happens. And I think the answer to that is this is what should happen given the principles governing the parts as they act in that arrangement. Okay. And it's the fact that there are covering laws that make it an explanation and not just a description. Okay. You could just have a description of what goes on and then claim that B occurs or this is what's responsible for it. But in order to get me to see it, generally what happens is there's an appeal to the covering laws or principles that govern the parts as they interact in the given arrangement. And I think this is the typical kind of mechanistic explanation. So this is, again, the example of the neuron signal transmission. When I looked at the, I can't remember now whether it was GCSE or A-level discussion of this. The students were being taught that signals within the neuron are transmitted electrically and between chemically. Now, what on earth does that mean? If it doesn't mean that, well, the signals within the neuron are transmitted by electrical interactions that we recognize as electrical interactions behaving in just the way we expect electrical interactions to behave. So a major player, and this is Coulomb's law, and the fact that electrons repel each other and that opposite charges attract each other. Then that's so there are highly abstract general laws, and then okay, so as I say, this is in accordance with the laws of electricity. For example, Coulomb's law plays a major role in this story, and of chemistry, which I'll leave to Robin. But at a lower level, then there are very low-level principles, very ceteris paribus principles that can be appealed to, and those are ones like we note in the diagram there. Okay. So this makes, as I say, the standard explanation makes extensive use of Coulomb's law. It also talks about diffusion forces affecting ions. Those are also in play, and they behave just as diffusion forces are expected to. How does the gate open? Well, a helical protein string with uneven charge distribution is contorted, opening a pore. In each case, the parts behave as they're expected in compliance with general laws, as they must if they were truly general laws. But, both John and I don't really believe in truly general laws that govern everything, no matter where they are, and so forth. But these are the kind of principles we've learned to expect when these features are present. Okay, so in this case, the explanation is both a mechanistic explanation and covering law explanation. Second example, John, I'm sorry, I've rearranged a bit. Don't be too shocked. One of the cases we do in economics is the Phillips curve, which is the trade-off between inflation and unemployment. And that has a mechanistic explanation, which is a covering law explanation. Simultaneously, what happens is the facts are they talk about the structure of interactions and agents. So what's in the model are agents with beliefs and who can interact. There are entrepreneurs and employees, representative agents for entrepreneurs and employees, and the agents interact in response to their perceptions of what's going on in the economy. And what actually happens in the model, that this is the Lucas model, is that agents believe that inflation is actually, they mistake inflation for real increases in demand. And so when they act in those situations to maximize profit, they open new jobs. Sorry, maybe that wasn't clear, but what happens is all these agents are acting in their own sectors. They see prices go up. They don't recognize it as inflation. They just see price rise in their own domain. And in that, so they think they'll make money if they make more products, which means they have to hire new workers to do that. So unemployment goes down. All of that's with respect to the structure, where agents don't know that it's inflation. So there's a second model, which is a slightly different structure, where it's the government that's controlling inflation. And in that model, it's impossible to conceal from the agents that this is, they're not mistaken about it being inflation. They see it as inflation. So the mechanism operates very differently, and still agents acting to maximize their profit under that law, they don't open new jobs. So both the standard Phillips curve, which holds for a long period and under certain conditions, and the breakdown of the Phillips curve, both have mechanistic explanations that are causal law explanations with slightly different structures to the underlying economy. Okay. Now, let's just turn to close to mechanist concerns about why some of the things that are published about why mechanists don't like causal law explanation. Craver and Taberry give a list. They claim that causal law explanations are unable to deal with causal explanation, that there's an inability to distinguish redescriptions from explanations that reveal the mechanism. There's a lack of depth, that they have a requirement for laws which may be unavailable in the special sciences, where nevertheless you can give mechanistic explanations, as I just said. And then the social scientists, George and Andrew Bennett, say that for covering law explanations, outcomes are supposed to be fixed by particular facts and laws. So let's look at some of these. The first one, inability to deal with causal etiological explanation. Well, both causal law explanations and mechanistic explanations should admit causal laws. There's not a, if you determine that there aren't any such thing as causal laws, you're going to have a hard time doing other kind of explanation. So I assume that both will admit causal laws. Now, this is to revert to something that John mentioned at the beginning. Sometimes these causal laws are the end of the story so far as nature goes. Some people think, for instance, forces cause motions. There is no further story to be told there. That causal law simply is, it just simply holds simpliciter. Okay? But sometimes the causal laws that we use and invoke are ceteris paribus laws, where the ceteris paribus clause refers to a mechanism. So the one I just discussed, rising inflation causes reductions in unemployment, very, very commonly used causal principle. And as I said, for a long time, governments tried to make use of it to help employment. And the ceteris paribus condition here refers to the kind of mechanism that I described. And so there's more of a story to be told. Okay, so the idea, the problem with causal laws doesn't plague nomological machine causal law explanations any more than mechanistic explanations, because the former, many of the former are mechanistic explanations on our account. So there are causal laws, can be causal laws appearing in the explanations in both, and sometimes these causal laws themselves can have further explanations, and sometimes not. Okay. So just to repeat, many standardly cited causal law explanations are mechanistic explanations. Many, I think that's back to front. Many standardly cited mechanistic explanations are causal law explanations. It's also, maybe it was a Freudian slip on my part when I was fixing the slides, because I was brought up, my introduction to causal law explanation was by Adolf Grünbaum, and then and all of the examples that I was brought up on of causal law explanations were mechanistic explanations, like the explanation of Kepler's laws by Newton's laws and the arrangement of the planets, and Hempel's own radiator example, which is highly mechanistic. Okay. Then concerns 2 and 3. And there's an inability to distinguish redescriptions from explanations and the lack of depth. Well, I think this is a fault of a claim about the causal law explanations. And it's the claim that a causal law explanation is all we need in science, or is complete enough to reflect all essentials that are going on in nature. Okay, we don't make that claim. Okay. Nomological machines were introduced in the first place when I was doing them, and then John started working on them. They were introduced in the first place to explain laws that themselves have explanations, as I said, and an example of that is Hempel's own Kepler's laws example. So we don't claim that causal law explanations are always all we need, or are complete enough to reflect all the essentials that are going on in nature. Rather, what we claim is that that a great many mechanistic explanations are causal law explanations, and that's part of what makes them explanatory. Okay. Concern 4 is the requirement for laws, which may be unavailable in the special sciences. Well, as John noticed, we agree that advances in the special sciences typically involve uncovering system structure, not laws. I think that's actually also the case in physics. That was what really mattered to understanding low temperature superconductivity, was not discovering new laws, but figuring out what kind of structure you could assign to the superconducting material to get it to behave in the model the way it behaved in reality. But the fact that advances in the special sciences and in physics can involve uncovering system structure rather than laws is irrelevant to whether general laws play a role in the models of why the systems behave as they do. Why does this system do what it does? Because this is just what must happen, or might be should be expected to happen if all its features act together according to the general laws governing them. And physics isn't special here. As I say, there's lots of examples in the social sciences. For example, even before, there's my old work on examples of socioeconomic machines, where you can find examples of money multipliers and debt generating mechanisms, as well as this stories about the Lucas models for the Phillips curve. Okay. Proceeding about laws. In fact, both John and I have been arguing that laws and principles are widely available in the special sciences. And we have to recall, even when we're thinking about the original covering law explanation discussions, Hempel, in his little book, Philosophy of the Natural Sciences, taught us that not all scientific explanations are based on laws of strict universal form. They may be probabilistic laws or tendency laws. Now, if they are tendency laws, this is one of the things that, one of the reasons I've got interested in this issue is if they're tendency laws, what more would you hope to have in the explanation in order for it to be a really good explanation of the behavior of B? Well, for a good argument that B is to be expected, if it's tendency laws that are involved in the operation of the parts, the facts may need to include the operation of triggers and of support factors and of the absence of defeaters, because tendency laws, aren't, this always happens, but this tends to happen. The part is disposed to do this, but it may need triggering, it can be interfered with, etc. Okay. And plus, if you're using tendency laws, you have also, as always, where the analytic method is in play, you have to have some principles about how tendencies in that arrangement combine. And again, this is something that I've been concerned about because in our little models in physics and economics, the laws of combination are very clear. For instance, in the mechanics one, right? What you do is you write down a force function that is associated with various descriptions of the structure, and then you vector add the force functions in order to figure out something you call a total force and use that to calculate an acceleration. So you've got a principle for how the tendencies, what happens when the tendencies all act together, when the parts with those tendencies all act together. But as Bill Bechtel has, well, many people, but Bill has been pressing it on me, the kind of models that we have of mechanisms are small world models, and the world is really a large world, and the actual things we're modeling are set in larger environments. And then there's a lot of things that aren't representable as forces, and they affect the behavior of the system. And what happens when all these things are operating together? That's a nice question, and that's one of the reasons for thinking about this being covering law explanation, is to try and address that question. Okay, fifth concern. This is from the social scientists. For causal law explanation outcomes, these two social scientists, by the way, they're process theorists. So they want to give causal process accounts rather than, step-by-step causal process accounts, as opposed to covering law explanations. And again, we've argued that the step-by-step causal process will often have, will need covering laws to justify what happens from one step to the next, and also probably need a mechanistic explanation underneath about why those steps are afforded. Okay. The thing is, we don't suppose that all causal laws are deterministic. Many laws used in causal law explanation are probabilistic or tendency laws. There's a predictivism objective. Probably we don't need to hear all this. CLE supposes predictivism. Sometimes Kaplan and Craver suggest that. For example, the barometer may predict, but does not explain the storm. But we don't claim symmetry of explanation and prediction. And one thing is to lay out a covering law model and to say that this model fits mechanistic explanations. Another is to make a whole host of other claims that were made about covering law models. Okay. There are 3 objections from Carl. This problem of distinguishing laws of nature from accidents. Well, I don't know. If you can't do that, you're not really going to get your mechanistic explanations to seem explanatory. And there are a number of ways on offer to select principles, like pragmatic laws, tendency laws, invariance account. But if you don't, if you think there aren't any principles, it's going to be hard to explain why I should believe that the electrons repel each other in the neuron. Okay. There's a problem of providing an account of explanatory relevance, and Craver addresses explanatory relevance by constitutive relevance. I mean, why is the mechanism relevant to the behavior? We to appeal to ontological account of the mechanism as a basis for solution of the problem of explanatory relevance. I think that what's going on in the world, in the situation that in the mechanism that the mechanistic model models is responsible for the behavior holding. Okay. We do not need to show the phenomenon is to be expected in order to explain it. So this is a quote from Craver. We have no difficulty in imagining quite irregular mechanisms, such as the mechanism for neurotransmitter release that works roughly 10% of the time, or rusty chainsaw that works arbitrarily infrequently. Causal law principles may be indeterministic or permissive in various other ways, and it's also that requisite features of the or the arrangement of the mechanism may not be in place when the explanandum behavior does not occur. Maybe there are some bolts are too loose to ensure appropriate arrangement on some occasions. So it's not a surprise. I mean, it's not at all a surprise that if you've got a rusty chainsaw, it doesn't work the way a good chainsaw works. And I'm really glad to see Craver saying that it might work. It might, you might have a rusty chainsaw, and there's no reason why it worked yesterday when I tried it, and it didn't work today, and it didn't work 2 days ago, but it did work yesterday. That's exactly the kind of permissiveness that I expect to find when tendency laws are at work, but most people really hold back from any such kind of permissiveness. Then Jim Bogen has an objection that the mechanistic explanation is the detailed description of the activities, and what matters is the activity in each instance, not what happens elsewhere on other occasions. So general principles are about something that holds, not just here on this one occasion, even if they're not, universal or don't hold everywhere. They're still the whole point was that they're that we've learned them as general principles that we can invoke across different settings. Though not, we may have to learn what kinds of settings those are. But Jim is worried that it's the activity in this instance that's relevant to the behavior, not what happens elsewhere. And it seems to threaten the idea that what happens falls under general principles. But Bogen's examples cite general principles. For example, fermentation turned out to be a physiochemical process. So the general principles may not be apparent on some descriptions of the mechanism, as we've said. For instance, it's not a general principle that pushing down the handle opens the valve. That's often one of the activities that happens that's the kind of activity that can happen in the description of a mechanism. It's not a general principle that happens, but the general principle under which it happens is usually something like the law of the lever. Okay. Conclusion. Okay. Describing the mechanisms, parts, structures, activity does not by itself show why B occurs. Okay. In many mechanistic explanations, this job is done by implicitly invoking principles that hold generally for the features of the mechanism, its parts, properties, interactions, and activities. There may be, as we admitted, emergent and perhaps other exceptional cases, but a great many of our most beloved mechanical explanations are covering law explanations. Thank you.